Well, I am delighted that Rudolf could join us again. Your last encounter at the e-research conference was outstanding. So I don't know how you're going to top up that one. But I'm delighted to introduce Rudolf Dimper. He is going to share with us his expertise in exploring new ways for staying abreast on any unprecedented data avalanche that we have seen to date. So the big data happening, and that's what Rudolf has been working on for a number of years. So Rudolf has earned his degree in chemical engineering in 1981 in Hamburg. His diploma work was done in the European Molecular Biology Laboratory on the design of real-time data acquisition system for X-ray muscle diffraction experiments. After his studies, he held a position at the Institute of Louvain, I cannot pronounce it, in Grenoble, to design assembly programs for real-time data display of neutron detector data, followed by a position at the Institute of Millimeter Radio Astronomy. Here, his work focused on software design for a radio wave correlator and in accompanying the construction of the Plateau de Beau radio interferometer, I can't say anything right today, which is 2,550 meters altitude, as the station manager. Since 1987, he works at the European Synchrotron Radiation Facility, where he held many positions in the Computing Science and Services Division. In 2004, he was appointed head of his division and member of the ESRF management team. In 2010, following an internal reorganization of the laboratory, he was nominated head of Technical Infrastructure Division, bringing together services encompassing the computing infrastructure, management information system, building construction and maintenance, electronics, the vacuum systems, as well as geodesy and alignment. So please help me welcome Rudolf Dimper once more to the research conference.
Yes, here it is. Oops. So, good morning, everybody, ladies and gentlemen. And so, thank you very much for inviting me again to come to the e-Research Australasia. It is a great honor being with you this morning. So, I'm German, living in France, working in English. Because I'm German, you will see that my presentation is very structured. So I would like to spend the first part of my presentation explaining what a synchrotron is, how it works. This is very important so that you understand then the science examples. I would like to give you a few key examples, very few, just to highlight what this instrument, being a synchrotron, can do to science. And then the remainder of my talk will focus on computing aspects. So let me start giving you a bit of an overview how a synchrotron works. The electromagnetic spectrum, you all have seen this in your education. Very important because this is really what governs what we see with our eyes, but not only. When you start at the lower end of the electromagnetic spectrum, you have radio waves. Those are detected by antenna. With these, you can then see molecules in the universe. Then going up the energy and going to shorter wavelengths, we have our eye. You can see that the visible part of the electromagnetic spectrum is really small. Then going again to shorter wavelengths, we have then electron microscopy. the synchrotrons come in with soft X-rays, hard X-rays, and at the extreme end, we have the colliders like CERN, who have extremely high energy and decompose matter. You look at particles directly. So synchrotrons, as you can see, work in an area of molecular and atomic resolution, and of course, our world is governed by atoms. We are actually constituted of atoms, and the way this is actually, the matter is organized is of course of fundamental importance to understand our world. Just to give you an example of how the wavelength actually changes our perception of the world, here we have the Earth in infrared. You can see the hotter and colder spots on Earth. In the moment, there's a lot of energy in the system with a little storm, unfortunately, on the east coast of the US. This is what we are used to look at, the visible image of the Earth. If you look at the ultraviolet, you can see that the Earth is completely different, being illuminated from one side from the sun, and having the ultraviolet rays being bounced off by the atmosphere. Unfortunately, we are protected quite a bit against the ultraviolet rays coming in. Extreme ultraviolet is again completely different. Here you see that the effect of the atmosphere, how it efficiently protects us. When we go to X-rays, the Earth is virtually invisible, but for the polar region, because of the magnetic field of the Earth, so again we have a complete different perception. And finally, gamma rays, in a very rare image of the Earth. Of course, here the resolution is extremely weak, but nevertheless, you can see that gamma rays, again, interact with the atmosphere. So you have the bright sphere around the Earth because of the depth of the atmosphere, which is giving an obstacle to the gamma rays passing by the Earth. Now, synchrotrons are tools to examine condensed matter, so everything which is not gases. So in fact, this can be tissues, this can be crystals, this can be metals, anything can be examined with synchrotrons, and this is why they are so extremely popular. They became extremely popular. Initially, synchrotrons were, let's say synchrotron radiation was a byproduct of high energy physics, but very soon it became the main target as an analytical tool to understand matter. Well, it all started with the X-ray tube. So here's one which has been savagely opened with a can opener, I suppose, to have a look into it. And what we are used to are usually the absorption images of our body when we go to the doctors, and we see that, of course, the bones absorb more of the X-rays than the soft tissues, and this is what the result is. Then you have an X-ray absorption image here of a hand. Would you do this with hard X-rays, because this is done with soft X-rays? You would, of course, first of all, inflict radiation damage to the hand, so that's not very nice. But you would also, again, see something completely different. You would not have the same image anymore. Now, what we are, of course, thriving at synchrotrons is to generate as much light as possible, because with the amount of light we generate, we can examine on a very short time scale. It's like with with photography. The more light you have, the shorter the exposure times. But also, we reduce the radiation damage overall, because radiation damage is in function of time. And I will come back to this later on. So what we are interested in to have more and more brightness or brilliance. This is the amount of light the synchrotron can generate. And you can see here that our laboratory has already increased over its lifetime significantly the amount of light we generate. And overall, we are now further than a little bit more than 1,000 billion times above the standard X-ray generator in a hospital. So you would not like really to be examined with such a synchrotron source, because this would essentially burn a hole into your body. This is where I'm coming from, in Grenoble, south of France. And this is just a bit of geography where this is, because, I mean, Australia is a big place and France is a small one. So it's south of France in a wonderful setting in the middle of the mountains. The place is framed by 2 rivers, 2 highways. This has definitely been done on purpose so that we don't have strange ideas of expanding further and spending even more money from the European Commission. You can also see that we are on a campus with many other laboratories. For instance, this thing here is a neutron reactor. This is the Institut Laue-Langevin, which Viviani has tried to pronounce, which is difficult. French is a difficult language, I know. And also microelectronics, for instance, ST microelectronics here. So we are in a busy site with a lot of interaction with many different domains, scientific domains and engineering domains. So the top view of this place. Now let me explain how it works. We have, first of all, to produce electrons, because X-rays are produced with electrons. Electrons are generated by heating a filament, which is put into a magnetic field, and you rip off electrons, and then they are accelerated in a linear accelerator. First of all, to 100 million electron volts. Then they will circulate in what we call the booster, where they are brought up to, not speed really, but energy. And once they are at nominal energy, they are injected into the storage ring, where they are kept as long as possible at constant energy, circling around and generating light flashes. How does this work? So first of all, the accelerator is composed of focusing magnets, bending magnets, and insertion devices. You need these elements in order to make sure that the electrons actually go around a circle, because they don't like to go around a circle. You have to force them. And you force electrons who are negatively charged by magnetic fields to go around, and this is why we need this magnet assembly. The bending magnets and the insertion devices are the devices which actually separate the light from the electrons. As I said, electrons want to go straight. If you force them to go into a bend, they lose energy, and this energy is lost in light, a light emitted in the forward direction. And this is exactly what is depicted here. So you force the electrons to go in a bend, and in the forward direction you have synchrotron light going into what we call the beam lines. Bending magnets generate a modest amount of light. What we are interested in is much more intense light, which is generated by the insertion devices, where the electrons have to wiggle through a constantly changing magnetic field. So they constantly change direction, and interference in the forward direction accumulates light and generates 1,000, 10,000, 100,000 times more light than in a bending magnet. And you get something like that, a spectrum, because it's interference. And what the scientists then do, they actually pick out wavelengths, which is at one of these maximums, to have the maximum amount of light, and adjust this within their experiment. Now, something completely else, something completely different. Electrons have to go around, not only in a closed circle, but precisely in a closed circle. They go around almost 300,000 times a second in our machine, which is almost 1 kilometer, speed of light. If you do the math, it's not really speed of light, because otherwise the mass of the electron would be infinite, as we all know from Einstein. So we have the bunches which go around at 350,000 turns a second. And at each turn, they have to be slightly corrected in the trajectory to make sure that they are precisely at the same position after each turn. The more stable the beam, the more stable you then can generate light, and the more stable you can set up your experiment and exploit the light. So this is very important, and we have made a big step forward with the Libera electronics, which is a commercially available electronic system which all modern synchrotrons now use, and which is actually a digital signal processor which allows you to calculate the ideal position and correct actually steerers, magnets in tiny values in order to make sure that the beam stays on track, perfectly on track and stable. And you can see the effect here in this graph. Now you see this is what would happen if you don't correct. and here a stable condition when you do correct. And what you have here is these little green spots are the insertion devices which change gap, changing the magnetic field, and this has an influence, of course, on the stability, but it's immediately afterwards corrected. And you can see from the scale that we are at sub-micrometer beam position precision, which is very good. A beamline then, where we collect the light, is used to condition the light. You select with the different optical elements the right wavelengths, the right position of the light, the right focus spot, so everything is adjusted there. Then the light is fed into the experimental hutch, where you have the sample, and then you have people sitting in the control hutch controlling the entire equipment of each of the beam lines. The sample generally is set up on an N-circle diffractometer here in this example, which should, by the way, be animated. Now, this is a 4-circle diffractometer where you can position a tiny little sample in space, 3 dimensions, have it turning without changing its position, and then measure with a detector the interaction between the matter and the light. Synchrotrons, as I said, became popular. There have been a number of synchrotrons constructed over the last years. In fact, more than 20 came up in the last 15 years. There are only, most of them are actually synchrotrons which are not at the energy we are at the ESRF, because the ESRF is an expensive device. Most of them at medium energy. There are only 4 places which are comparable. The one in Chicago, the APS, which is running at 7 GeV, 7 giga electron volts. Then we have in Japan, Spring 8, which is an even bigger machine. A new one, brand new one, is situated in Hamburg, Petra 3. They have converted high energy physics accelerator into a synchrotron, and they got the funding for this lately. And then you have the ESRF, of course, the nicest and most successful place out of those 4 big synchrotrons in Grenoble. Now let me go along now for a few science examples showing you what you can do with a synchrotron. And this is really, just to say it again, a selection. It is a tiny selection of what is possible. Now, first of all, to introduce this, again, I want you to understand how important it is to understand matter, because this really is the link to how we interact with our world. The Stone Age already showed that once we were able to fasten the stones, that we can build tools, then things can evolve. In the Bronze Age already the weapons could be produced, and again changed quite a bit how mankind evolved, not necessarily in the right direction. The Steel Age then was another step where engines could be produced and the real industrial revolution kicked in. One can say that today, unfortunately, we are in the oil age, trying to burn all our fossil resources as much as we can and as fast as we can. And pretty soon, or maybe already today, we can say that we are in the silicon age, where we are driven by semiconductors and screens. So matter matters, and understanding it is fundamental. We have now major societal challenges in front of us. We have screwed the planet so much that, to my opinion, the only way forward is science. We have to compensate for what we have done, the way we are living, not necessarily, or certainly not in equilibrium. And only research can give us the possibility to go ahead, develop our societies further, and maintaining our way of living. This, of course, feeds essentially into health, energy, and material science. And here is exactly the role of synchrotrons. Let me give you an example of life sciences, which are of extreme importance these days. More so even because we are looking at aging populations all over the world. A good example is X-ray diffraction on crystals. And when we say crystals, very often we mean proteins, which can be crystallized. What happens if you have a crystal and you put it into beam, the photons are actually diffracted and you get a diffraction pattern. This has been shown by Max van Laue a long time ago already. And you can use these diffraction patterns, if you turn your crystal and you collect a certain number of these patterns, to reconstruct the structure of the crystal, and from the structure of the crystal you can then determine how the actual molecules look like. This is what is done extensively in protein crystallography and macromolecular crystallography. The last 20 years have been very much dominated by this research at synchrotrons. Now what happens, since most of the easy targets have been done, the crystals are smaller and smaller, and it becomes more and more difficult to put them into the beam due to their size. Proteins do not like to crystallize, really. And that's one of the issues we have to attack massively in order to continue and thrust forward in life science. The 2009 Nobel Prize was won with the structure of the ribosome. The ribosomes are these little red dots here, which you have sitting here in the endoplasmatic reticulum, and they are these little factories which produce proteins, and the proteins are, of course, what we are made out of. So it is extremely important to understand how the ribosome works. If you do, then you can design drugs. You can design specific drugs which interact with the proteins manufactured in those ribosomes. So the team of Vanke, Mr. Thomas and Ada have worked on this on the synchrotrons Ada Ionat, in particular at the ESRF, and they managed to determine this structure, which for a normal mortal looks like a heap of spaghetti, but for a life scientist, extremely exciting. Of course, much of this work has only been possible for two things. One, the experimental conditions on synchrotrons, but secondly, the computing which we have behind. And for instance, the data analysis capability based on GPUs in order to process the massive amounts of data which are generated. Here you have a little animation which shows you how the ribosome produces proteins. The team here at the ESRF during their work. Another example, also extremely important, and this is the 2012 Nobel Prize in Chemistry. It deals with the G-protein coupled receptors. G-protein coupled receptors are fascinating systems which allow to communicate from the outside to the inside of cells via the cell membrane. In fact, many signals need to pass there, and this is the way we actually can see, we can look at images. This is the way we function when we smell. This triggers reactions, chemical reactions, and the chemical reactions are actually passed on to our cells. And this is where these G-protein coupled systems come into place, because they are the messengers from the outside to the inside, vice versa, to the cells. So this team has worked over the last 15 years and on these systems. And 10 years ago, Kubilkar started his work at the ESRF because it was the only synchrotron being able to do this type of work at that time. And then later on, he continued his work in the States at the APS. So the 2012 Chemistry Nobel Prize, and here a little picture of how the structure looks like, and some of the mechanisms, how the cell membrane is actually traversed by signals and based on the proteins. A completely different subject, and here we go into the imaging technologies, computed tomography. Tomography consists of taking a series of pictures, either for medical purposes or not necessarily, or for other image reconstructions, where you look at an object and you try to get a 3D volume of the object. So it was initially used for the computed axial tomography applications in hospitals. And we have a medical application, we have several medical applications at a synchrotron. One of them focusing on breast cancer, for instance. And breast cancer cancer, of course, is one of the important topics because, unfortunately, in the US alone, 40,000 people die every year due to breast cancer, and not only women, by the way. Unfortunately, CT scans cannot be done on soft tissues because of the high radiation dose. You would actually inflict bigger damage than what the method would actually result in gains. So the only way forward to do this is to use hard X-rays, which in the moment you don't have in a hospital, but we have at a synchrotron. If you look with hard X-rays at the breast, you can see unprecedented details while reducing significantly the radiation dose, actually by a factor 40-50, and get extreme high-resolution images of cancers. And here is an animation showing you this. Of course, this as a diagnosis tool, and then for chirurgy, for operations, this could be extremely helpful. The issue now is how to get a synchrotron into the hospital. You have to shrink wrap the synchrotrons, but work is actually going on to have tabletop synchrotrons which could produce relatively hard X-rays to do this type of medical applications. And yet another application, again, on health science, and this concerns 3D phase nanotomography. Just to explain you the principle here, you have the sample sitting here on a spindle, which is normally not of wood, but this was a nice way to depict it. The spindle is able to turn, but also to change position. The hard X-rays come in here through a mirror system where you select the wavelength and you position the beam. You have a tiny little sample. The tinier the better, in fact, in order to go to higher resolution, and then a high-resolution electronic detector here, which takes the images while you turn the sample, taking one image after the other. Typically, what we do is for a single volume, you have to take up to 4,000 or 5,000 images and then reconstruct the volume. Again, all these are high-resolution images. You can imagine the amount of data this generates, and then you can look at what this gives you. In the case of the bones, for instance, which are fascinating material, our bones, we don't realize this because we're just taking this for granted. But if you magnify and you go down to molecular, almost molecular level, you can appreciate how structured and how hierarchically organized the bone is. And here is a little image which shows this. You have the big structures, and then we have taken a sample here, which is tiny, which is something like 400 micrometers across, 5 millimeters high. And you can then see these lines, little cavities, and then also bigger lines. So this image here is just this little enlargement coming from here. But in the bigger images, you see also this, what we call the cement lines, which gives the structure of the bone. We're now going through this little sample with slices. You can discover the cement line here, and then cavities and other fine structures in the bone, osteocytes and channel systems. And then, this is the next one. Again, the sample, you can actually, because you have it all in the computer, subtract parts of the 3D volume and have, for instance, the channel system appearing in 3 dimensions, the cavities and everything, and understand how bones are actually forming or how bones are destroyed, because many of the bone diseases, like osteoporosis, for instance, of course, then things don't work anymore and you start having dysfunctional structures which have not the same mechanical properties anymore. So again, here we have an example which was only lately done, where the findings have now a direct impact of what happens in new medical applications to interact with bone diseases. So here's the result, for instance. Then, of course, you can construct the models. You see here very nicely the cement lines. This is what the major stability gives in the bones. And then this channel system here, which is extremely important for the mineralization process in bones. Something completely different, going on with the science examples. You know that in chemistry, what is very important in order to have chemical reactions going on is our catalysts. Very often chemicals don't like to react, so you need catalysts. And here again we have the possibility with a synchrotron to look at the way the mechanical reactions happen in real time. So here I don't have an animation, but what is important is to understand how to optimize catalysts, so you have a good feeling of what this means when you change your exhaust pipe on the car, because there are some pretty expensive metals in your exhaust pipe these days, hence the cost. So it would be great to do it differently, not with platinum, but with other materials like, for instance, nickel, which are cheaper and which could last much longer. So there is quite some industrial challenge. And it's not by coincidence that I will not show you the results of this research, because this is industrial research, which of course then has quite a bit of proprietary issues and confidentiality issues. In the similar direction, biocatalysts will play probably a major role the way we drive cars later on, because biocatalysts will allow to generate energy from water. Of course, water has hydrogen, and hydrogen can be used to power our cars. However, there are many effects which make it very difficult to have these chemical reactions under safe conditions, and to understand the catalytical processes in all details. Again, here the impact would be fundamental in terms of energy consumption in transportation. And a last example, glass. We know glass very well. Why is this an important example? Because glass is actually constituted of silicon dioxide, sodium carbonate, and calcium carbonate. Usually, what the glass industry does, they mix the grains of these three constituents, then heat the mixture, and they heat it over a very long time to have homogeneous glass, because the glass forming process has never been very well understood up to now. That results in an extremely high energy consumption while producing the glass. So here we have done studies at the synchrotron, looking at the sample, the glass sample. And here we have the grains, which are of variable size. As you can see, for instance, here for the sand grains, 160 to 200 micrometers. Then the sodium carbonate, a bit bigger, and the calcium carbonate. Then we look at a sample which first of all is examined, a first volume, and we can slice through the volume, understand how the grains are actually touching each other. And this is what goes on here. So one slice after the other going through this three-dimensional volume. And what is interesting then is to follow the glass melting process while you turn up the temperature. Now you turn it up to not 1,500 degrees, but just until the glass melts to understand what's going on. And here the process. For each of those temperatures, 3D volume can be made, and you can see what happens to the grains, how they melt into each other. And as you see that the glass melting process actually takes place between 800 and 900 degrees. So there is no necessity to go much higher. You only go much higher for a simple reason, because there are some defects which would appear if you wouldn't. And then your glass is not completely transparent, but has sufficient defects that it starts to be opaque. And that is one of the outcomes. In fact, what is important here is the last line, that if the calcium carbonate grains are not sufficiently in contact with the sodium carbonate grains, then you have defect formation. And this is the reason why the glass industry heats up to 1,500 degrees for hours and hours and hours to get rid of these defects. The glass industry uses the equivalent of the Netherlands in terms of electrical energy. If we would make half of that saving, you can see the impact. Again, industrial research directly applied here from a synchrotron, so a major impact for industry for the future. What is a nanometer? We have seen examples which are at micrometers, some already at nanometer resolution. It is important to understand what this really is, to appreciate the difficulties we will have in the future research we are doing at synchrotrons. 1 meter, we are very accustomed to this. A medium-sized girl is 1 meter. The tip of a ball pen is a millimeter. If we go further down, the blood cells, 7 micrometers. And when we look at nanometers, here the DNA, the distance of the 2 strands of the DNA, in fact, are at 2 nanometers. 2 nanometers correspond to 20 atoms, approximately. So this is what a nanometer is. You can also compare it. If the nanometer would be a cherry, and then a meter would be the Earth. So just to look at the dimension, we talk typically about nanoscience whenever we are below 100 nanometers. So what that means that we are looking at 1,000 atoms at that resolution. We have a very nice example, which is already in our everyday life, and this is electronics. The electronics industry has diminished size. Every generation of processes has a size which goes down, and we are now looking at 20 nanometer transistor sizes already. You can see that this trend has a limit. It has a limit when we reach the size of the atom, and clearly then the electronics industry has to invent something completely different, and this is why we unavoidably will go to quantum mechanics and quantum computing in the near future. So nanoscience will be the new future, the new frontier in synchrotron science. And of course, there are some fundamental challenges when you do this. If you just simply imagine that you have a sample, which is, let's say, 100 nanometers, you can't see it anymore with your eye. You can barely see it with a microscope, if ever. You need an electron microscope. How do you position such a sample in front of a beam of light to make sure that the beam of light shines through? Not at all easy. The beam of light has to be stable. If it vibrates and you illuminate and you're in and out, then you have a problem. So you need extraordinary experimental conditions in order to be able to do nanoscience. And this is the real challenge we are now confronting, having extremely stable experimental environments, be it temperature, be it vibrations in our laboratory. For instance, our air conditioning system has to stabilize the temperature in all rooms at 1/10 of a degree, summer or winter, which is not easy. The ground has to be stable, such that if somebody walks, your sample does not jump up and down at the scale of nanometers. So you can imagine what that means. And then, of course, bizarre as it may appear, the smaller the sample size, the more data we generate. Why is this? Because then we blow up, of course, the image. We have demagnification on very large detectors, and because we are looking at phenomena which also in time become very short, we look at real-time phenomena. We are filming then chemical reactions, for instance. The data rates just simply become extraordinary. So I will conclude the scientific part of my presentation just showing our publication record in a lab like the ESRF. We are approaching 2,000 publications. Many of them, in fact 10%, are in high-impact journals every year now. So you see the scientific impact of such a laboratory. So not surprising that every country, every continent wants to have a synchrotron. There is a real driving force in terms of scientific output behind this. Now let me go to the computing part. How to survive actually in front of all the data we have, and what does that mean in terms of challenges. First of all, the basic numbers. We have at the ESRF not one experiment but 40 experiments working simultaneously. We already multiply the amount of data we can get by 40. We are having 6,500 to 7,000 scientific visitors coming in every year. We are a service laboratory. They come with their sample, set it up, measure, and disappear. At least that is what we thought. These days they're not disappearing anymore because we want to analyze their data also. As I said, 1,800, pretty soon 2,000 publications every year. And today, about 4 terabytes of data every year, structured in tiny files of about 1 million every day. And when I say every day, I mean 365 days a year. It's a non-stop operation. We have from time to time interruptions in order to optimize the synchrotron to intervene. But overall, it's a non-stop operation 24 hours a day. To highlight what the data explosion means, here is a good old friend of us, Sahelanthropus chadensis, a skull which was found in Chad and which has been measured at the ESRF in 2004. In fact, the overall data set represented 4 terabytes of data at a resolution of 45 micrometers pixel size, so over this large object, 45 micrometers each pixel. Would we do it again today? What would we do? Obviously, we would measure the same skull with, let's say, 10 times higher resolution. If you do 10 times higher resolution, the output would be 100 times 10 by 10, in fact, 1,000 times higher. So we would look at a considerable amount of data today. Why would we do this? Why would we measure with higher resolution? Such an object sees a synchrotron only once in a lifetime, maybe really only once at all. Now, you wouldn't see it a second time. It disappears then somewhere in a museum and is not coming back. We had this same effect for another skull coming from South Africa. This was Sediba. You may have heard about the Sediba skeleton, which was found in South Africa, another ancestor of humankind. Again, it came once to our place. It was actually guarded by South African policemen, and those policemen were standing around the experiments area while we were measuring the skull. You can see how important these artifacts are. Again, just to highlight what happens these days, usually what we are doing now, we do scans over a 3D volume, and each intersection of the line here represents a pixel. Now, what we are going to do in the future is that we subdivide the volumes once again, and that we make a scan of each of those little cubes represented here. And that means, of course, that again, by a power of 3, the data volume would increase, and we would look at terabytes and petabytes by doing this. And this becomes, of course, in particular dramatic if you look at very large objects. This is all driven by modern detector technology, the stuff you have in your cameras in order to take pictures. This is industrialized, and we have these large high-resolution detectors, which are faster and faster. This is very important. So the next generation will be able to take thousands of pictures a second at high resolution, and this is what generates really the data avalanche. Now, HPC comes in order to allow this to happen, so that the experiments taking place are not slowed down or made impossible, because behind this, the computing environment does not respond anymore, because you can't process the data anymore. 2 aspects here. One is to fight latency, the time it takes to look at the data, to store it, simply to dump it to disk. And then, of course, functionality, because it's simply not the same whether you produce 1,000 files or tens of millions of files. It's not the same. You simply sometimes want to do a directory listing with 1 million of files in a directory, and you know what I'm talking about. Where are we at the ESRF with this challenge, fighting latency? We have a high-performance network. That is not a problem, and we are proud of this network. We have plenty of 10 gig network links all over the place, so there's plenty of bandwidth. Where we do have a problem constantly is writing data to disk. Making backups sometimes is extremely difficult. Managing these very large file systems. We will have, at the end of this year, we will have a petabyte file system. The data analysis, how to do the data analysis quickly enough to follow the experiment, because most of it is done online and has to be done online in order to judge where the quality is of your experiment while you are doing it. So in terms of data storage, we are looking at NAS systems. Unfortunately, they are not that scalable. If you buy one of those, then you have 2 controllers controlling a bunch of disks. and this determines the bandwidth you have. So we are looking at scale-out solutions like individual servers which are dedicated, but then it becomes again difficult to manage the file systems. Then what about processing data fast? Again, this is very important because people come to a synchrotron when they have made a proposal, they have prepared the sample. Sometimes it takes them years to prepare a sample, and then they get 3 days of measurement time at a synchrotron. So it is extremely important that the data processing is fast and taking up with the measurement process. And it's increasingly difficult for those people to take their data home. They don't have the infrastructure there to store a petabyte of data, let's say even tens of terabytes of data, and the same for the analysis environment. Brute force doesn't work anymore, you know this. The processor capacity is not increasing anymore. We have to parallelize. And parallelizing, we have 2 issues here. We can subdivide a given process into bits and smaller pieces. This is easy if you have individual images because you can work on one individual image, but not always. This is not always the solution. Sometimes you have to decompose this further and do real parallelization, and then of course it becomes a bit technical, and this is where we need the IT expertise really. The classical parallel programming is like everywhere else, OpenMP, MPI. Let me zip through the slides because I'm running out of time. You all know about Amdahl's law. It's nice to parallelize, but if you have a sequential part in your program which is not parallelizable, then this will determine how far you can actually gain in time. So if an application is badly written, then even the parallel version stays quite poor performer. And then there are, of course, bottlenecks. For instance, I/O bottlenecks. How fast do you get your data into the processor or out of the processor? I/O bandwidth is a big deal, is a big problem. Now, this is not a French highway because you would see the cars trying to fit into the other lane because they want to gain a few seconds on the neighbor. Batch schedulers are important. Many of our scientists now are confronted with batch schedulers. We have selected one which is a derivative of PBS, and it's named OAR. It's a terrible abbreviation, and in fact it's stemming from PBS just shifted by 1 letter. So another way of finding acronyms. So developed in France at the French Institute for Applied Informatics, nifty functionality, quite heavily used. We are quite happy about this. And then we are looking, of course, into parallel structures like GPUs massively. We were very lucky that many of our programs could be parallelized. We had a few engineers working on this the last years with stunning outcomes. For instance, here's an example which is quite important. When you adjust a sample in front of the beam, you need to do online data processing to see how well it is in front of your beam. And you can see the performance increase between the classical approach here with the Intel CPUs and here on GPUs. You get performance increases in the factor of 20 to 50, which changes completely the way the scientists work on the beamlines. And then, of course, simulation is extremely important because in upfront of your experiment, you have to already understand what's going on. And here again, we are looking at applications like the density functional theory, which is used, by the way, as a benchmark for the Praise supercomputing installations in Europe. We are very lucky to have this gentleman, Luigi Genovese, with us at the ESRF, continuing his code developments. Now, let me zip through a few slides which are nevertheless important. The European Union has invested a significant amount of money into data management, and you can see a number of those initiatives here on this slide. You may wonder how this will all fit together, and I do also wonder with you how this will fit all together. We are involved in 2 of these initiatives. One is the PAN Data Initiative, PAN staying for Photon and Neutron Initiative. bringing together all the synchrotrons and all the neutron reactors in Europe and getting our act together how to manage data, in fact. And that's, I can tell you, a difficult one. Here's a picture of these different research infrastructures. There was quite a bit of investment in these research infrastructures. Another of these projects is CRISP. And CRISP is coming from the S3 roadmap, preparing new projects on the European landscape. And again here, we are joining forces and trying to look at data management, how to harmonize our data policies between all these different laboratories, to look at how we authenticate and authorize scientists to come to our lab, how actually interact with the people, then how do we preserve the data we have. In the moment, data just disappears in drawers, as it is the fact for many research activities, and so on. So this is a very ambitious program, but very important also because scientists do not anymore use one single facility. They use several facilities and they want to combine their data sets in order to have a result. And one of the examples I very much like is paleontology. For instance, here an example where a single piece of amber, opaque amber, has been analyzed and to look for little insects which have been trapped in there 100 million years ago. So nice to have a view back, not only to look at current problems. And these little elements, these little insects have been extracted virtually and put into a database and now are publicly accessible. And this is, for instance, here a dragonfly, or here in this example, a little tiny spider. Again, very high resolution images. These insects are tiny because otherwise they wouldn't have been trapped in amber. 100 million years old, and you can imagine how excited paleontologists are to look at these specimens in order to deduct evolution of these species. So let me conclude. First of all, I hope I have convinced you that synchrotrons are nifty tools to do a lot of important science. So there are many, many applications of enormous potential. Information technology underpins what we can do or what we can't in the future. The complexity is very quickly increasing and we need gifted IT staff. This is something very important. In the moment, we have tendency of losing staff to industry and even worse to finance, and this is something one has to make sure it doesn't happen. In particular in the UK, there's a very bad trend in the moment. Something more important even is that policymakers must understand how important science is, and they are all now tempted to cut science funding, and that's probably the worst one can do. What we really need is to have stability in order to develop the tools, in order to have visibility how the funding will be the next years, in order to retain staff, but also simply to run large-scale infrastructures on a stable way. And last little picture of my home place, my home laboratory, and let me thank you for your attention. You were very patient with me. A nice picture of the Grenoble environment. The synchrotron is sitting here. You can maybe see it. In Grenoble, the Grenoble area, and this is where I spend my weekends in the mountains with my wife hiking. So I'm very lucky person to be in this area, but I'm also a very lucky person to be here in Sydney and visit Sydney. Thank you very much for your attention.
Thank you very much, Rudolf. It's an incredible presentation. It's amazing. Thank you for sharing your expertise and giving us a glimpse of what you go through every day and the challenges you're facing, which are similar to challenges being faced here. We ran out of time for questions, but we have morning tea now, so I think we should at least take a couple of questions, if anyone has any questions for Rudolf. We have a roving mic in the middle. That's unusual.
They're all exhausted.
You drank too much last night. So I do have a question. So with all of this amount of data that is being generated, and obviously all of the challenges you're facing, how do you see us managing data and sharing it in the near future? Let's not go too far.
Sharing data, I mean, I would say there are technical aspects to this problem which can be overcome, which may need funding, but again, this can be overcome. The most important hurdle we face in Europe and maybe also in other continents, it is the same. They are sociological. It is extremely difficult to convince scientists to give up their data, their property of the data, and make it publicly accessible. And this is where we need help. We need the help of funding agencies, of policymakers, that making research data publicly accessible after a certain embargo period is mandatory to obtain new funding for new experiments. We are struggling with this in the moment, not only at ESRF but also in the other laboratories, to set up the data policy, which must be coherent because it cannot become a competitive argument where the one lab allows people to go away with the data and the other one forces people to publish the data. So I think the sociological aspect is the main one. And then, of course, and only in the second instance, then the IT aspects come in, which are solvable and which are extremely interesting to tackle. And there are some interesting aspects, but doable.
Thank you very much. Well, this is just a small token of appreciation.
Thank you very much.
Help me, thanks.
Thank you.